everyone, this is Yujin Li. Welcome to my dsa5205 Project 1 presentation. This project reproduces and extends the virtue of complexity in return prediction by Kelly. In this 10-minute screencast, I'll walk through how the entire pipeline runs reproducibly in a clean environment and explain the key results from task 1 to 3. On the left, you can see the project structure, scripts, source code, configs, and outputs. To ensure full reproducibility, I recreated a makefile with separate targets for environment setup and each experiment. For example, I can type, this is a fresh environment, and I can type make setup conda to create the conda environment and then simply run make task 1, make task 2, or make task 3 to execute each script. This design allows staff to reproduce every result with a single command. And now it shows my environment already exists. Now I have to activate it. Okay, now it is activated. Before running the experiment, let me quickly show the project structure inside the source directory. Each file here corresponds to a logical component of the pipeline. Simulate defines the data generating process, and models implement the ridge and lasso estimators, also including the elastic net and PCR, also PLS, used in task 3, and metrics, which computes Sharpe ratios and are square consistent with the paper. Pre-process standardizes and aligns real data features. Selection implements prefix cross-validation and the one standard error rule. And importantly, the plotting provides consistent figure style. This modular design makes the entire project easy to extend and fully reproducible. Now let's start with task 1. This script implements the ridge regression simulation. It first loads configuration parameters from configs task1.yaml file. You can see here that this YAML file includes C, training and testing length, true complexity sen, which says to be 10, and grades of Q and Z. Then inside the nested loop over Q and Z, it generates data via simulate.full function, applies partial observation with observe partial function here. You can see, and fits rich models using rich fit dual, computes metrics R square, expected return, Sharpe ratio, and beta norm square, and stores the results into task 1 metrics.csv. After aggregation, the plotting function plots R2 with CQ, and all these plotting functions draw the characteristic double descent curves. Now let's run and see what kind of results. Okay, it is now finished. We can see that in the output figures, here we can see the double descent pattern around the CQ equals to 1, which matches the original KMZ findings. As complexity increases, performance first dips then recovers when regularization stabilizes the fit. We can see the trend is same for expected return, beta square, R square, and Sharpe ratio. Now let's start task 2. Well, task 2 extends baseline by replacing ridge with lasso regression. The structure is almost identical, same data generation loop, same metrics, but now we sweep alpha values to induce sparsity. Let's execute it. Okay, it is now finished. Let's see. This is beta square, expected return, R square, and Sharpe ratio, and volatility. The resulting figures show smoother Sharpe ratio curves and bounded coefficient norms, indicating that L1 regularization controls variance and selects useful feature automatically. Comparing with task 1, we see how explicit sparsity improves stability in high-dimensional settings. Now let's move on to task 3, where I worked with the real financial dataset A, B, and C. Before modeling, I performed a brief exploratory data analysis to confirm that feature names align between training and test sets and to remove constant columns. This step is here. Then the script performs the 5 key steps: load, preprocess, and standardize data without leakage. You can see it here. And secondly, perform prefix cross-validation. Use grid search CV prefix. This is written in the selection.py file. Third, apply the one standard error rule to select simpler models, also written in the selection.py in the source code. Fourth, evaluate each model, ridge, lasso, elastic net, PCR, PLS, OLS, and finally save the validation logs and test predictions. Let's run it with make task 3. And you can see that the best model for each pair is printed to the terminal, while predictions are saved to outputs hidden right here and here, right? And now we use the Jupyter Notebook to visualize these plots. Let's rerun this thing over again. You can see that the PCR model consistently achieves the highest Sharpe ratio around 8 components, confirming that moderate rank representation generalize best. It's same for pair B and pair C. And the best parameters we choose is shown here. The reason why for dataset B we choose a linear model is because of the one standard error rule, which is illustrated explicitly in the report. So I'll skip this part. To summarize from this experiment, task 3, I learned how important proper model selection is in financial prediction tasks. Even though complex models like ElasticNet or POS can fit the training data well, they tend to overfit when feature to sample ratios are high. The prefix cross-validation and one SE rule help me understand how to trade off bias and variance systematically. The PCR model's success shows that using a few principal components captures the dominant risk factors while filtering out noise. In other words, moderate complexity, not too simple, not too flexible, generalizes best. This helped me connect the paper's theoretical idea, the virtue of complexity, with practical implementation and model diagnostics. Well, to summarize and conclude all 3 tasks, this project is fully reproducible through modular scripts, configuration files, and makefile pipeline. From task 1, I learned how model complexity and regularization interacted to produce the double descent phenomenon. From task 2, I saw how sparsity enhances robustness. From task 3, I confirmed that careful cross-validation and the 1SE rule yield stable out-of-sample performance. Altogether, the results validate the virtue of complexity framework and demonstrate full reproducibility. And across all tasks, I learned how model complexity, regularization, and cross-validation jointly determine generalization. Reproducing the KMZ framework gave me a hands-on understanding of bias, variance trade-off, and how to make machine learning models in finance both interpretable and robust. Thank you for watching, and all this is written in my README file. You can see all in my GitHub project.